So good afternoon, everyone. Let us start discussion regarding image geometry. In the last class, I have introduced you this concept of image geometry. So image geometry actually appears in the form of spatial relationships between pixels or groups of pixels. I'll repeat. Image geometry appears in the form of spatial relationships between the pixels or groups of pixels. So in the last class, we have seen what we mean by spatial relationships between the pixels. So if I'm having the image like this, let us assume that we are having 5 rows in the image and 5 columns in the image. Now so this is 5 by 5 image, let us assume. So if I'm having this particular pixel, right, then the spatial relationships between the pixels or groups of pixels, what does this mean? So we are having different kinds of relationships, spatial relationships between the pixels or the neighborhoods. So if I'm talking about this particular pixel, then this, these are 4 neighbors, right? Horizontal and vertical neighbors, 4 neighbors of this particular pixel. This is also known as 4 connectivity or 4 neighborhood. If I talk about 8 neighbors, then I will consider these 4 neighbors along with the diagonal neighbors also. So this and this. So these will form my 8 neighbors for this particular pixel, right? So typically whenever we discuss about image geometry, it appears in the form of spatial relationships between the pixels. So these are the spatial relationships between the pixels in terms of neighborhoods. So for this particular pixels, these 8 are the neighbors, or if we consider 4 neighborhood, then these 4 are the neighbors, right? Now typically the geometric operations actually change the relationships between pixels by moving to some new locations while preserving to some extent the pixel neighborhoods. What does this mean? Whenever we are performing geometric operations, right, then what we are trying to do is we are trying to change the relationships between pixels by moving to the new locations, right, by moving to the new locations. But to some extent we are preserving the pixel neighborhoods. So if this pixel is being shifted from this particular position to some another position, then the geometric operation actually tries to preserve the pixel neighborhood. So if these are the 8 neighbors of this pixel, the same pixels will be there in the neighborhood, right? So the geometric operations not necessarily always, but always tries to maintain or to retain or to preserve to some extent the pixel neighborhoods, right? So geometric operations change the relationships between the pixels by moving to new locations while preserving to some extent pixel neighborhoods. And geometric transformations are necessary if the imaging process suffers from some inherent geometric distortions. So I have explained this concept in the last class. Why actually the geometric transformations are necessary. So if in the imaging process there is some kind of geometric distortion, right? Maybe let us have one example. Suppose this is one image, okay, and in this image suppose I am having this particular object, okay. Now if, or rather let us say that I have acquired the image and I'm having the object like this. So if I have acquired the image, then this imaging process has suffered from some distortion. Like this object actually I wanted to have in the vertical orientation, but whenever I captured this image, there is some amount of tilt. There is some amount of rotation or tilt with respect to this vertical orientation. So if I would like to process this image further, right, what I need to do is, before going for processing it further, I need to correct the orientation of this image such that this object would be placed vertically, right? So I may use some kind of rotation here, and I may come up with the vertical image, and then I'll process this image further, right? So if inherently, if there is some kind of distortion in my image like this, then I would use geometric transformation, right, such as rotation, to have the image appropriately placed vertically with respect to the orientation. And once I have done this pre-processing, then I may go for further steps in my image processing task or image processing application, right? So this is how many times we need to make use of geometric transformations, right? Right. Now, one more application that we may find for geometric transformation is image registration. Anybody who knows the task of image registration? Yes? Many times we come across the task of image registration. So image registration actually pursues the goal of bringing some common features in two or more images into coincidence. What we mean by that? Suppose I am having one image here and another image here, right? And suppose I am having the object partially available here and partially available here, right? So many times, or this kind of task is also known as image stitching. So what happens is, the entire object is not available in any of these two images. So what I need to do is, I need to use some geometrical transformation operation, right, such that I can bring the common features of these two images together, right? And what I can do is, I can use that operation to stitch these two images or to register these two images or one image using these two images. Right? So many times it happens that whenever I'm having this image and whenever I'm having this image, maybe in this particular image, my object is appearing here with some dimension, and the same object partially is appearing in the other image, right? But whenever I'm acquiring that image, maybe my object is not exactly at the same position, but my object is like, this is the other image and the same object is appearing somewhere here, right? So what I need to do is, I need to appropriately move that object to appropriate location, and then only it would be possible for me to relate these two objects to come up with one single object using these two objects, these two images, right? So here also we need to shift the image, or we need to perform some geometric transformation so that the common features, the common components, the common points in these two images can be correlated. Right? So these are several applications wherever we need to use imaging geometry. So the common geometric operations are scaling, translating, rotating, reflecting, and affine transformation. So these are the geometric operations, common geometric operations. So what is scaling? Scaling meaning changing the image content size. Scaling operation is actually performing change with respect to the size of the image. Then what is translate? This operation is meant for changing the position, image content position. Right? So changing the position of the object is nothing but translation. Rotation, changing the image content orientation. So just now I explained you actually these two, translation and rotation, right? Shifting the image or part of the image, rotating, changing the orientation of the object, right? So if the in the original image the object is tilted by some angle, then I can rotate it. Right, I can perform geometric operation rotate so that the orientation of the object is as per the requirement. Then the next operation is reflect, so flipping over the image content, and then the affine transformation, so general image content or maybe the combination of these transformations are there in affine transformation. Okay, so we are going to look at the details of these operations along with the examples. Okay, so let us first look at the operation scale. So geometric transformation, scale is the geometric transformation which can be used to shrink or to zoom the size of the image or part of an image. I'll repeat, this operation scale is the geometric transformation that can be used to shrink or to zoom the size of an image or part of an image. Right? So let us see this example. So what we have here, we are having, this is my original image. Okay, and this is my result. So what I have done, this is my original image, and what I have done is I have used shrinking operation, right? And see here, this object S is being shrink here in the output. Okay, so we are having two kinds of operations under scaling, and these two operations are usually known as subsampling or shrinking, okay, and zooming. So what is subsampling? Subsampling actually deals with image reduction. So it is performed by replacement or by interpolation between pixel values in a local neighborhood. I'll repeat. Image reduction is nothing but subsampling or shrinking. Right? So by making use of this method of subsampling, we are trying to reduce the image with respect to its size. Okay, so it is possible to reduce the size of the entire image or even some part of the image. So image reduction is performed by replacing group of pixel values, right, by one arbitrarily chosen pixel value, or it may happen by interpolation between the pixel values in the local neighborhood. So we will see what does this mean. Okay, and zooming actually is achieved by pixel replication or by a method called as interpolation. So let us see first the methods of subsampling or shrinking. So see here, suppose this is my original image. This is the original image. Right? So this is some part of the image. Right? Now, I'm using or I want to shrink this image. So suppose this is my 4x4 image and I would like to come up with a 2x2 image. So I would like to have half of the size of the original image. So 4x4 converts into 2x2. So if I'm using the replacement with upper left pixel policy, then what I'll be doing, see here, this is my 4x4 image. Okay, I would like to convert it to 2x2. So I'll be shrinking it. So what I'll do, this is first subpart. So I'll be selecting here 2x2 neighborhood. Here also 2x2 neighborhood. Here also 2x2 neighborhood. Okay, and here also 2x2 portion of the image. Right now, from this 2x2, what I'll do, I will pick the upper left pixel. So this 2. From this region 2x2, I will pick the upper left pixel. So 2. From this region, once again, from this 2x2, I'll pick this, and from this 2x2, I'll pick this. Right? So what I'll be doing is, from these 2x2 regions, I'll be picking only one pixel, and that is the upper left pixel. And I'm coming up with this output. Right? So 2, 2, 2, 2. So 4x4 image is being converted into size 2x2. Right? I may go with interpolation also. So interpolation using the mean value. So how I'm going to do that? Interpolation using the mean value. So first this 2x2 region I'll be considering. So here the intensity values are 2 plus 4 values 2, 2, 6, 6. So 2 plus 2 plus 6 plus 6. So it comes out to be 16, and mean of these 4 values. So mean is 4, right? So what I'll be doing, at the place of these 4 pixels, I'll be using 1 pixel, and the intensity value for that pixel is 4. Mean of these 4. Now here also I'm shrinking. So for these 4 pixels, I'll be having only 1 pixel, and the intensity value would be the mean of these 4 quantities. So once again it is 4. Right? So this is how the 4x4 image gets converted once again into 2x2. Right? So these two are the methods those we may go with for subsampling, right, or shrinking. So replacement with upper left pixel, and this is interpolation using the mean.
Yes, ma'am.
Right. Now typically scaling is used to change the visual appearance of pixel. So it has been used to change visual appearance of image. Right? So, or you may say that it can be used to alter the quantity of information that is being stored in an image. Right? So many times these kinds of transformations are used for pre-processing. Right? So I hope you must have understood this subsampling or shrinking method. Now, the next will be focusing upon zooming. So it is also part of scaling method. So see here, we'll be focusing upon once again two methods here, nearest neighbor interpolation, or it is also called as replication method, and the other method that we will be focusing upon is bilinear interpolation. Okay, so let us first see this nearest neighbor interpolation. Nearest neighbor interpolation. Sometimes in literature, it is also called as zero order hold. Okay, so see here, we are having this original image of size 3 by 3. So this image is being written in the form of a matrix, 3 by 3 matrix. So this is my original image. So what I want to zoom this image. Right. So original size is 3 by 3. I would like to zoom this image by size 2x. Meaning I would like to have the output as 6 by 6. Correct? So I'll be using the method of replication. So what I'll do? So here I'm having the intermediate image. So image with rows expanded. What does this mean? So actually I'm having 3 rows here with 3 columns. So I'm expanding the rows, meaning the rows are same, 3 rows, right? But the number of pixels now, originally 3 pixels, 3 columns. So I'm expanding the row, meaning I'm expanding in terms of number of columns. Okay, so what I have done is, this is replication method. So consider this row, first pixel is 69. So the same pixel gets replicated here, 69. Next pixel is 50, 50. So it gets replicated as 50 once again. Then it is 80. So once again, it gets replicated as 80. So 3 columns in each row. Now it becomes 6 columns in each row. So image is being expanded such that the rows are expanded. So 3 columns are now 6 columns. Okay. Now in the next step, what we will do, we will expand the columns. So what does this mean now? See here, in each column now, in each column, I am having 3 values. Right? Now I am going to expand the column, meaning the first value in this particular column is 69. So I'll be replicating one more row, right, with value 69 in this particular column. Now the next value is 45 in this particular column, first column. So 45 also gets replicated as 45, and same is for this 30 value. So now I'll be having in every column, now I'll be having 6 values. So columns are now expanded. So earlier in each column I had 3 values. Now I am having 6 values. So this is my final image with rows and columns expanded. So the zooming is 2x zooming. So 2 times the image is being expanded with replication method. So every row, in other words, you may say that every row and column gets replicated. Okay. Now, the other method for zooming is bilinear interpolation method. So once again, we are having the same input, original image, size 3 by 3. And what I want to zoom this image by 2. Okay, and I'll be using another method which is known as bilinear interpolation. So what I'm trying to do here is, please see here, simply I'll be using the mean. Okay, I'll be using the mean. So what I'm trying to do here is, see here, I'm having these 2 columns, first 2 columns. 69 and 50. So what I'll do, I will compute the mean of these two values, right? Mean of these two values, and that mean is being inserted here. Is that okay? Then once again, the mean is being computed and it gets inserted here. Right? Similar is the case, mean of these two values and that gets inserted here. Mean of these two values that gets inserted here. Okay, so image with rows expanded will look like this. So now here I am having 3 rows as it is, but the columns are now 5. Okay, the same procedure we are going to apply to expand the columns. Okay, so how I'm going to do this? This is my column. Okay, so this is my column. So I'll pick this and this value, and average of these two gets inserted here. This and this value, average of these two gets inserted here. So this is how I'm having now this value 57 and mean of these two 45 and 30. I'm having this value inserted here. Are you getting me? Yes.
Yes, ma'am. Yes, ma'am.
Right. Now, what is the size of this image, output image? Is this 6 by 6? What is size of this image? This is my output image. What is the size of this?
5 by 5, ma'am.
This is 5 by 5. Right? So, using such kind of a method, I'll be having the size of the image. If original image is of size m by n, then I'll be having 2m minus 1 by 2n minus 1. That is the size of my zoomed image. Okay, now if I would like to have 6 by 6 image, right? Because I'm zooming it by 2x, then I'm expecting the image size as 6 by 6. So how I can do that? To do that, what I'll do is I will use one concept that is known as padding. So padding meaning adding new column or row into the original image. Right? Or rather in this particular image. So what I'll do next is I'll add 0 padding. Okay, I'll add 0 padding. What does this mean? Meaning I'll assume that I'm having here a column like 0, 0, 0 and a row like 0, 0, 0. Okay, so what will happen then? I'll be using this value also, and I'll be finding out the mean of these two values and I'll put it. Okay, then mean of these two values and I'll put it at the appropriate place. Are you getting me? So padding is one way to come up with the size as expected, that is 6 by 6. So I may pad one row and one column in the original image, and then we will be following the same process to come up with whatever is expected. Example of zooming by these two methods. So this is the top row and this is the bottom row. So what is there in the top row? So image, original image of size, actually I have seen this showed you this picture earlier. So if I am having the original image of size 128 by 128, then that is being zoomed to size 1024 by 1024. This is original image of size 64 by 64 and it is zoomed to once again the size 1024 by 1024. And this is the original image is 32 by 32 and that is being zoomed to size 1024 by 1024. Correct? Now this top row is actually showing me the result of replication, okay, or the nearest neighbor interpolation, and this bottom row is actually showing me the result for bilinear interpolation. So right now we have seen these two methods. So see this row and see this row. So by replication we'll be having such kind of image, and by bilinear interpolation after zooming we will be having such kind of image. Okay, so here simply we are replicating the things. Correct, na? So if I want to go from 32 by 32 to 1024 by 1024, then how many times I am going to replicate? 32 by 32 for this particular column. Original image is 32 by 32, right? And after zooming, I am having the output as 1024 by 1024. Correct? So what is the zooming factor here? It is 32x. Correct?
Yes, ma'am.
So what is happening? In original image, I am having 32 by 32 image. So each pixel, so instead of this pixel, I'll be having in my output, what I'm having in my output, what I'm having, this is a single pixel in my 32 by 32 image, right? I would like to have 32x zooming. So what I'll do, this pixel gets replicated 32 by 32 times. What does this mean? So first 32 rows and first 32 columns will be replaced by this intensity value. So if this is my intensity value, say A, then all this block, entire block, 32 by 32 block gets replaced with this A. Why we are clearly, or why such kinds of blocks are clearly visible? Right? So the entire 32 by 32 block is having the same intensity value here. Is that correct? And that is why we can visualize here the effect that is known as checkerboard effect. Right? Whereas in case of bilinear interpolation, the effect that is evident here is a blur. So here we are able to see the blurring effect. So we are not replicating the pixel value as it is, but we are manipulating the pixel value and then that pixel value is being replicated. Okay, so we are having here some kind of a blurring effect in the output. So we may say that the bilinear interpolation or bilinear interpolated images are smoother than those which are resulted from this method of replication. So if we compare this image and this image, or this image, or this and this, right? More checkerboard effect is evident in replication method, whereas the bilinear interpolation method is giving us the smoother result than the replication method. Right? So many times whenever we are zooming the image, we go with such kind of bilinear interpolation or even sometimes cubic interpolation. We are not going into the details of other methods. There are several methods for zooming. Right? So I hope the idea is clear. Okay, so let us proceed now with the next geometric transformation operation, and that is translate. So what this operation is, translation operation. So this operation maps the position x1, y1 of each pixel in an input image into a new position x2, y2 in an output image. Right? So what this operation is doing? This operation is mapping the position x1, y1 of each pixel in an input image to new position x2, y2 in the output image. Right? So see the example. So this is my original image. Okay, and this is the translation operation. So just focus upon this object. So this object is being translated to some other position. So each pixel x1, y1 is placed at some new position x2, y2 as per requirement. Right? So typically the mathematical operation that is being performed is like new position x2 is being computed as x1 plus beta x and y2 is computed as y1 plus beta y. Right? And this beta x and beta y values are being given, and those indicate actually the shift in terms of x direction and the shift in terms of y direction. So depending upon this x and y, we are simply shifting the position of the pixel. Is that okay? Yes. So all these transformations are actually the spatial cases of affine transformation. Right? Spatial cases of affine transformation. The affine transformation will be focusing upon the affine transformation a bit later. Right? The translation operation is also being used to improve the visualization of the image. Right? So typical application is to improve visualization in some cases. And this is also being used as a pre-processing task. Right? So many times for registration of 2 or more images, such kind of translation is required. Right? So I hope the concept is clear. The next operation that we are going to discuss is rotation. Right? So this operation maps the position x1, y1 of a pixel in an input image onto a position x2, y2 in the output image by rotating it through some user specified angle theta about origin O. I'll repeat what we are doing here. So this is also a transformation function. So what we are trying to do here, we are trying to change the input position x1, y1 of the pixel to new position x2, y2. Right? And this is being transformed by making use of the rotation operation. So we are rotating the image. We are making use of some angle theta. Right? And by that angle theta, we are going to rotate the image. Okay. Now let us see one example here. So see here, this is my original image and I have rotated that image. Right, through 90 degrees theta. Okay, and I'm having now such kind of image. So simply I have rotated this image. Now mathematically how this operation is being performed. So note down this formulae, right? So the output x2 is being computed as cos theta into x1 minus x0 minus sin theta into y1 minus y0 plus x0. And y2 is being computed as sin theta into x1 minus x0 plus cos theta into y1 minus y0 plus y0, where this x0 and y0 are the coordinates of the center of rotation in the input image. Right. So if I would like to rotate this particular image with respect to origin or the center of this image, right, then whatever are these coordinates of the center pixel, center of this image, those are denoted as x0, y0. Right? So x0, y0 are the coordinates of the center of rotation in the input image, and theta is the angle of rotation with clockwise rotations having positive angles. So if I would like to rotate the image clockwise, then my theta is positive. If I would like to rotate my image anti-clockwise, then my theta is negative. Right? So once again, such kind of rotation operation is also used to improve the visual appearance of an image. And typically, this is used for pre-processing, as I stated earlier. Okay. Next operation is reflect. So what this operation is, geometrically transform an image such that image elements, that means the pixel values located at position x1, y1 in original image, are reflected about a user specified image axis or user specified image point into a new position x2, y2 in the corresponding output image. So see here, this is my original image and this is the reflection or reflected image. Okay, now the horizontal and vertical reflection about some point x0, y0 in input image is given as this. So mathematical expression how to compute x2 in case of reflection. So x2 is equal to minus x1 plus 2 into x0 and y2 is given as minus y1 plus 2 into y0. What is this x0, y0? Horizontal and vertical reflection about some point x0, y0. So we are defining some point x0, y0 with respect to which we would like to reflect our input image either horizontally or vertically. Right? So whatever you are looking at right now, it is vertical reflection. Is that okay? Yes, you may say this is a mirror image or flipping, correct? Affine transformation. So this is actually one of the important classes of linear two-dimensional geometric transformations, which maps the variables For example, the pixel intensity values located at some location x1, y1 in input image to the new variables like x2, y2 in the output image. And for this, we are applying a linear combination of translation, rotation, scaling, and or some non-linear transformation also like shearing. Right? So in affine transformation, we may have this series of geometrical operations. Say for example, if this is my original image, right, and I'm using affine transformation with respect to this original image, and I'm coming up with this output, right? So if this is my input and if this is my output, then I have not used one single geometrical operation, but what I have used is I have used scaling as well as rotation. Do you agree with me? I have scaled this A, right? So I have zoomed this A by some factor, and then I have rotated this A, and I have got this output. Correct? Right? Do you agree with me?
Yes, ma'am.
So in affine transformation, we may have one or more operations, those are performed in subsequent phases to come up with the output. So once again here, my pixel x1, y1 in original image is being shifted to or is having a new location, say x2, y2 in my output image, right? But not necessarily I am simply using scaling or simply using rotation or simply I am translating it, right? But I may use several combinations of these geometric transformations. So any combination I may have. So here in this particular example, I am having scaling plus rotation. And that is why we said earlier that all these transformations, scaling, translation, rotation, can be thought of as the special cases of affine transformations, right? But typically in affine transformation, we may have the combination of these operations to come up with the result. One of the applications I may quote here in satellite imaging. Such kinds of affine transformations are really required, right? Where we need to geometrically correct the ground maps. So maybe in satellite imaging, we need to perform such kinds of affine transforms, right? Where we need to geometrically correct the ground maps. As per our requirements, right? So several such operations we need to perform. So I hope you must have understood all those geometric transformations.